Alright, coding time. So this stream is for entertainment purposes only. Today we're gonna try to solve another coding problem under 40 minutes, hopefully. Unless it's a hard problem. Then we're just gonna try to waste 40 minutes of our time. Uh, and we're gonna do this as usual, real time. So let's just see what the problem we've got today. Alright. Internet seems a bit slow here. Alright. Pick one. Almighty randomizer. Okay, it's a medium problem. Bitwise ORs of Subarrays. Sounds interesting. People like it, so let's see what it is. We have an array of non-negative integers, okay. For every contiguous subarray with I less than or equal to j, alright, not sure why it's important, we take the bitwise OR of all the elements in sub obtaining a result ri blah blah blah, return the number of possible results that occur more than once or only counted once in the final answer. Straightforward example, array of 0, 1. There's only one possible result, 0. 1, 1, 2. No, wait. The possible subarrays are 1, 1, 2. I see. 1, 2, 1, 1, 2. These yield the results 1, 1, 2, 1, 3, 3. There are 3 unique values, so the answer is 3. Alright. Now I see. So sounds like a little bit of recursion plus. So the recursion in the sense that how you split it on subarrays, right? So 1 is 1, 1 is 1. Bitwise operation of 2 is whatever. It's like with 0, right? Alright, so it's 2. So then we have 1 and 1, so obviously it's a 1, right? Then we have 1, 2, and in this case, 1, 1, 2, and then 1, 1, and 2. All right. So the problem with this approach, like just brute force search through basically all possible subarrays and take these ORs and, return the unique elements, is basically, so I think it's something like on sliding window here too, because it sounds like, so you shift it one element left or shift it one element right, and then you do a lot of recomputations, right? wonder if there is an easy algorithm than that. So, I mean, they could have get any operations like plus or something, right? They said or. The reason they use or, not and, or, is, all right, let's switch to the whiteboard first and see what's the unique about or operation. Let's consider this array, right? Like we have an example. Let's use it as 1, 1, 2. So from that, let's say we have obviously 1, 1, 2. Then subarray is 1, 1, and 1, 2. Then subarrays of these are 1, 1, right? This is the same element, and 2. So, and let's see, so let me write down the 2 in binary, right? The 1 and the 1. So this is basically what we have initially, right? So we say or between, it's not technically or, because it should be vertical, but whatever. So this gives us what? At least, if at least 1, 1 we have in the integer, right? It will be 1, and same is here. So the total is 3, right? Now if we have this only, is also 1 and 1, it's 3. And if we have this only is 1, right? And this only is 2. So the thing is, here is interesting stuff. So we can't throw element from the middle, right? It should be consecutive. So really, my understanding is what we really need to do, we need to take, let's say, first element, or we can write it like this, second, third, right? Sorry, third. We don't have 3 in the binary format, sorry about that. 1, 0. So can it be just a simple cycle where we start with first element, right? Once we go to the second element, it's the what? The or of this, and no. So the key word here is not how we traverse, is the or operation, right? So we shouldn't go, my understanding is, so you see the num is from 1 to 10 to the power of 9. So we shouldn't really go all the way through all of the elements, although we might too. So this is 50,000. There is a lot of binaries. So I doubt we should go like element by element. But let's see. So obviously the first thing is all right, so focusing on this thing, right? So what unique we can say. So obviously every element we can just go directly and put in the set all of the integers we have in the array, right? So it's not a big deal. Then if we're gonna add one by one an OR, right? End up 3. At this stage is keeping 1, 1, 1, so it doesn't change anything. But once we go to this, does it really important what was here? Yes, I think it does. Is it sorted, by the way? No, it's not. Interesting. So the solution is screaming it should be something like all right, so first step, put everything in set, right? So this is simple example when we just have one subarray, which is just one element. So we don't really care about that. So it sounds like n log n, right? Or with each other is the same. But then we might miss. So my idea is that we can split it like this, right? We can split it until we have the 1. But the problem is, if it's, let's say, 1, 1, 2, 3, 4, right? We can just take this and this, and then this. This would be ideal n log n solution, near linear solution, to do this, but it's not the case. The problem with that, we might miss opportunities like this, right? And assuming we never had 3 here, and let's say it was 5 or something, then we potentially may miss one of the elements. When going through every bit, what we can notice that if we have at least 1 here, then no matter how many elements we add to this subarray, this will remain 1, right? Same here. Yeah, I don't understand. So this OR operation, is there any benefit? So we can try So what it tells me basically is that you can for sure just do or of two recursive calls, right? And this will be the same as going through subarray one more time, so you don't need to recompute things every time. Plus you can memo in the middle, so let's say memo of this subarray or that subarray, but it's not the point. The point being, oh man, is that in this case, if we go, let's say on the first call we have this array and this array, right? Then we have what, 4 elements only, and then we have 3 options how to shift this window, right? For here, or like this. So the number of subarrays, so number of calls will be n, and number of subarrays in every call will be n. So it will add to n squared. So n squared is easy, no doubts. N squared is super easy. But I doubt that n squared is gonna help us. Is there like even, okay, let's, so how much time we have? Like 15 minutes span. Even in the example, they go through all combinations here, which is quadratic, right? We have 3 elements here, but then 1, 2, 3, 4, 5, 6, or okay, maybe it's n squared divided by half or whatever. Or something, right? But still, it's not linear. The problem with this is, oh man, yeah, the problem is it's quadratic, so we won't pass the 10 complexity check. So n squared is easy, and it will require us, I would imagine, yeah, it's hard to say how much space it would take, because we will count unique numbers, right? So how many unique numbers can be if it's 10 to the power of 9 and 10,000 elements, so maybe also 50,000 square-ish. Okay, let me see the hint here, at least in terms of dynamic programming. Okay. Dang. Stupid dynamic programming. Yeah, it makes sense that this is dynamic programming, but dynamic programming is usually quadratic too. Okay, for dynamic programming, I don't see any easy way of saying, I mean, I just said that the subarray that consists of 2 elements that are included already, right? It's just OR operation for all of these elements. So you don't need really to go through all of them and recompute over and over and over again. Like it's easy, but maybe then it's just all right. Let's see if it works. Let me just assume here that we have unordered set of integers. Let's call it unique, right? And then we have private method. Let's call it subs or whatever, subs. So what it will do, it will tell me let's say it will tell me let's say we have, it can be const vector here, right? Array. We also have unique as the, let's say, as reference, and we might have int ij, which is basically start and the end of it. All right, in j. All right, so if j minus I equals 1, so what do? You say unique insert array I and return array I, right? Else. So if it's larger than that, then we say int a equal and subs, right? Or we can call it subs. Subs. So we either need to add I plus 1 j or subtract 1 from j, right? So I array, obviously unique, and then I j minus 1, right? So we always subtract from j. Or same thing, but now it's I plus 1 j, right? Then we say it's not going to work as fast as they want us to, but at least I understand that we will parse all possible subarrays, and that's the problem. So you don't need to definitely you don't want to parse all of them, because it will take hell a lot of time. It's 10 to the power of 4, right? So every time we do 2 calls here, and we keep branching, and basically it linearly reduces in size until we hit 1 element. So number of such calls will be n. But the good news, every operation here is the constant, but the number of such operations still linear, so it's quadratic, unfortunately. Insert a return A. And then here, we say subs. You can ignore the output, array, what unique, 0, and array size. And then we return unique size. So this is a very simple algorithm, all right, which basically just traverses Windows back and forth and does this OR. Because it's OR, we are okay to do it like this, because the same element with itself or element does nothing, right? So technically, here is the thing. So basically we want only count all unique numbers, the OR operation between all unique numbers. And this means, so we might not need even to go through all subarrays, technically, right? It's dumb to go through all subarrays, because let's say, like in example 2, we have 2 1s. We don't need to consider 1 and then 2 1s. It's the same result. But we do want to consider 1 and 2, because those elements, combination of those elements are unique. And so maybe this what we want to do, maybe we just want to track indices of unique elements or whatever, and then see so alternatively, maybe we can make a pseudo-polynomial, like we go, okay, this order, let's say that decides either 0, 1, 2, 3, 4, 5, 6, 7, 8, so 2 to the power of 8, and so forth. And then try to understand. Alright, let's first see that at least something is working here, because we just have 10 minutes. Slightly more than 10 minutes. Yeah, it works. Then let's make sure that it won't pass time complexity check, because it won't. Yes. So how much test we've passed with this dumb solution? 55 out of 83. Okay, I see. Right, so it works, but it's super slow. As I said, it's quadratic. Although it's very simple to understand. So the dynamic programming they want from us. So the problem with dynamic programming, you need to find the key to the problem, right? So what are the keys we have here? Well, the array is allowed to be consecutive, only one thing. And second thing, it's OR operation. So non-unique elements does not add up to the final result. And to me, this sounds exactly what we need to do. So All right, so we have just thinking about dynamic programming. So what do we have? We might have the array of positions, right, where we start our subarray. And we might keep adding to those position element by element until we hit the maximum, right? And count unique elements as we go. Maybe that's the thing, but still you have array and you will add element by element to this array. So it doesn't sound like, it still sounds quadratic. So it doesn't really tell us anything. Now, so if we go with the idea that we track unique elements in the array, right? And then for every unique element position, we have it's still, even if it's non-unique, it still can affect the results of other subarrays just by combination with. Yeah, but maybe we won't be able to track the subarray. All right, so it's not what we need to do. Oh man, this dynamic programming is killing. So let's return back. So at least we have some sort of solution that doesn't pass all the tests, but pass more than half. So it's something. So okay, we know it's dynamic programming. We know it should be, in worst case, near linear thing, or linear better, right? Which means, can we really go just one pass through this, keep adding stuff to it, like we have this 0 1, right? And we know that, say, the second element so we have this, we have this, we have a combination, then the third element, and then we have 0 1 here on the side, right? And then we say we have the 0 2, which we add here, which we add here, and then we have 0 2. All right. Oh man, this is dumb. All right, so it's 1 0 1 0 1 0. So in this case, I do see. So this will give us 1, 3, 1 and 3 from this. From this we will have only 3, and from this we will have 2. And the number of unique elements is 3, right? So the problem is that for every element we have, so let me rewrite it in this way. So we have 0 1 0 1 1 0, right? So this is our array, let's say. So we don't do anything, and then we keep adding stuff, this element to this element, right? And will it cover all of the elements? It should be, yeah, it should be. And here we have 0 1 1 0. Here is 1 0 1 0. So something like this. So this is n. This is, and every time we go in this cycle, so we go, it's n squared, so it's still the same. I don't know how to make it linear though, or near linear. I do see a lot of redundant operations. That's what I see. So the one key to dynamic programming here that I see is the OR operation, saying that if we have array of, like in this example, 0 1 0 1 and 0 1 1 0, right? Their combination is the same as do 0 1, right? So we don't care about these non-unique elements, and 1 0. Alright, we are running out of time. We have 2 minutes left. I still don't come up with any good dynamic programming idea. So label correction. So label correction works in this case, right? But it's still quadratic. It's technically a label correction. Once you count for this, you can add element and do OR operation for this cell, and then another OR operation for this cell. Then this, 1, 2, and then this, right? As a result, we should get all of the unique elements by adding elements to every cell of initial numbers. Yeah, I don't see. Yeah, I just don't see. I mean, dynamic programming is always like this. I would imagine that once I will go to the discussion and find the first algorithm with the dynamic programming, 1 minute, I got the key, it's clear. It's clear, it's simple and straightforward, and nothing really hard. But right now, I don't see it. So that's the problem. I just don't see it. At least we had the solution. So, all right, let's stop here. switch back to the default scene first. Oh no, let's directly go to the scores. So we'll first fix the scores. So it's 55 test outs of 83. Zero. Another 0 and 55 out of 83. So not really happy today because it's medium problem and we haven't solved it technically, right? Or at least we solved it suboptimally. So let's just see what was the key for dynamic programming. Because dynamic programming, I mean, memorization technique can be one I'm thinking about. Yeah, I don't know. All right, so let's see. What? Java and Square solution and still passes? For God's sake, I had a Square solution. Why it didn't? Is it in Square? I mean, every time we subtract one element at a time. So every time we go one level beyond, the subarray shrink by one element. So we have n sub steps to get to one element only. It's in Square, yes. So let's see what's the beat. Damn, the beat. So the thing is, because it's integer, we technically should track 30 bits. Okay, yeah, not 32 because it's unsigned. Because we have only positive integer, so we're fine with 30. And to do this 30, I believe it's greater than 10 to the 9, right? So 30 is fine, yes. So alright, so that was the data structure. I thought about it when we discussed this possibility of just checking one digits, right? Because once the bit is, is filled with something, we don't care anymore about this bit, because it won't give us a unique solution. So let's see. We go through the n. In minus 1, so in the reverse order, because we want so, maybe, I don't know why, but whatever. So if specific bit of the element, right, is 1, then we say it's I. How? This element, yes. So what we track is which element has which unique bits. That's clear, right? And if it's 0, so it's not 1. Then we say it's equal to the next element. Interestingly, why? and I is greater or equal to 0. So if I is n, we have n plus 1, so it's okay. So the bit will be, bit is the same. Yeah, you see, come up with something like this. This is this key source here for the dynamic program. So first of all, you should, okay, we almost got the idea that we want to track the uniqueness of the bit for, let's say, every element, right? But this thing, do you understand why it should be the bit of the next element if the current bit is 0 for the current element? If the current element is bit is okay, then we just track this I, right, the position for that element. I don't know, but whatever. So we have created this data structure, and it will allow us to crack now in linear time. I see. Yes, we have this encoded set where we just track the unique elements, so we have vector pairs, but not, I don't know why we need it so far. So we go through bit, and then we go through the pairs. For every I, we go through all possible bits. And I would imagine I corresponds here not like really to the specific element in the array, but more like to the size of the subarray we are considering. And obviously then you have all bits equal to 0, I would imagine. This is my case. But if no elements, nothing. So then, interesting, we do sorting. And when we sort pairs, we sort based on the first element. Yeah, not very trivial. I would say it's more like hard problem to solve than easy problem, because I mean, for the if they were okay with quadratic, then yes, it's medium, no doubts, maybe even easy one, or like in between easy and medium, because you still need to do bitwise operations. You need to do, but dynamic programming with this weird structure like this, that okay, you don't do bitwise, you're screwed. But even this, like you don't track the unique bits for subarray sizes you can get, you're screwed. Then you also have sorting. So you see, it's yeah, I mean, pairs are the size of bit, so the sorting will take bit log bit times this, so it's near linear complexity. It's not quadratic though, it's near linear, and I was surprised that Java beat in quadratic complexity, passed the time complexity check. In pairs of the size b, right? pairs j first equals n break. Right, so we reached the top of everything. Value or, because this is addition, you can just add it to the current one, is 1 pairs j second. So so we track that the bit was 1, right, or not, and we just shift it to this and add it to value. So we add this unique 1, and then we do what? Okay, so I got it. So we track unique bits in every element first, and then we do this interesting combination to adjust to value for every pair's length. Interesting. And log n solution, yes, and simple one. Set and dp set. For every I in array size, we just insert array I to the temporal. Then for every n in dp set, so this is n, and this is should be log n. We say insert temp, insert array I and n. So set of integers, right? We have one value in temp. And then once, so every time temp has just one value, and the current value is whatever prior elements in set we had, right? All right, so let's say 2 elements now in the next episode, then 3 elements, 4 elements, 5 elements. This dp set will contain unique numbers every time. And we only take into account the unique numbers. Alright, makes sense. Yeah, this one is way easier. Actually, this one, yes, this is the medium. If you can understand that set can track you the unique elements. And then all you need is every new element that you try to add to track if it changes something. But I wonder though, if you're missing out. No. Okay, so every unique element is basically any start point for the next subarray, right? Okay, yeah, makes sense. And it's n log n, yes. Great. So this solution is awesome. That one was a little bit more complicated with these things. This one is cool. But oh, you haven't seen anything, whatever. So that one is great. So there are two solutions I've seen. So one is Bitwise, with very complex data structure, a lot of cycles, and you need to spend a lot of time to understand why you need to sort, let's say, beats and stuff. And basically the same thing, oops, that's way simpler, just two sets that solve the problem. One tracks unique elements, and then other one tracks unique elements that can be encountered from 0 position to whatever you achieved, right? So this will basically give you all combinations. super simple. Super simple. Just two sets. Yeah, I didn't figure it out actually. That was the key for the dynamic programming here. As I said, it's OR operation, right? That we need the unique elements, and whatever was before, you just do it OR with current element to see if it adds something new. And if so, all I need to do in this case just drag this new element and use it for the next element we consider, or with all other prior elements we have so far. But I wonder though if this thing can result. So if we have elements like 1, 2, and 3 in the set, and we had like 1, 2, 3 in the set, or maybe 1, 2 in the set, right? And 3, of course, it won't be unique. Can we then, once we go to the, let's say, 3, right? Can we have what? Yeah, 1 and 3 won't do anything. Or let's say we had 1, 2, and 4, right? And then so my concern is that it may not necessarily be consecutive subarray if you have the DP set. It may assume that, let's say, you used first element in this DP set, which was obviously might be unique, right? Then there were some other elements in the DP set, right? And because we insert whatever element in DP set we had, or array I, we might technically consider, let's say, fifth element here combined with first element. It may create a unique element which was not allowed otherwise, or which would not happen otherwise. Is there a guarantee that we won't do this? Alright, we start with what? With DP set that is from the product. So initially it's empty. So the first thing, we just have element 1. We add it here, right? Okay. And then we add it here. Okay. Then we go to the second element in the array. And then we say, okay, second element is the second element by itself, because obviously it might be a unique one, and the combination of it with the prior element we had, right? So now you have first and second element and second element. Then we go to the third element. We do again the third element by itself, then third element with first and second, and with second. I see. Yes. There's no way is every time you add on the OR operations there, right? Yeah, great. I mean, this is awesome. Right, so with that, see you tomorrow.